Hi, I'm Michael Hansen and welcome to another one of my videos. At first I would like to make some announcements. I have been relatively inactive regarding to physics and particularly regarding flat earth and globe earth and all that jazz. I've not been completely inactive on my channel because I've uploaded several gaming videos. That's another one of my passions, is computer games. So I have uploaded some videos there and you are of course very welcome to check them out. Some of them, particularly the game The Long Dark, is in Danish. I might do a series in English, but I thought that there are already many videos out there about this game in English. So I would do something for a change in my native language. I've also thought about making a series of, let's say, high school physics videos in Danish. Again, because there are lots of videos out there on YouTube and other channels which deals with high school and entry-level university physics in English. And definitely with teachers that are much better than me at doing this. So I'm not even going to start to go there. But of course I'm trying to upload some videos about sort of my specific field, astronomy, particularly gravitational lensing, but also I'll try to find time to continue with my videos on photometry using IRF or PyRF. It's basically the same, but it's just the interface. Yeah. So the reason why I have almost stopped, I might do a couple of videos on it, but the general reason I've stopped doing videos with respect to flat earthers and globe earthers and all that is because I was actually I was a member of several Facebook groups, and I noticed two things that, to be honest, annoys the shit out of me. The first thing was about me. I was in the group Flat Earth Society, I think it's called, a Facebook group, a discussion group. And I noticed when I came to that group, I came with that idea and that philosophy that when you discuss with people, you treat them with respect, you treat them nicely, no matter how idiotic claims they make. That was my entry philosophy, and I took notice, but initially didn't jump on the wagon that several others in that discussion group mocked people, make fun of them, use nicknames for them, call them idiot and all sorts of things. And as time went on, I noticed some things in there. First of all, whether they were trolls or actually flat earthers, they kept posting the same idiotic memes, the same idiotic pictures, and the same idiotic claims. And I found out with myself, inside myself, that first of all, when you have that environment where everybody is calling you a flattard or retard or something like that. For example, there was sort of a saying that woke is the new retard. But never mind about that. I noticed that being in that environment and feeling that I actually got annoyed with having to give the exact same response to the exact same stupid memes, I myself began to call people names. And I became more rude in my way of treating people. So at some point I just found out with myself that I wouldn't want to be a part of that anymore. So I resigned from that group. One other thing I noticed, but that's particularly in the Danish groups I was a member of, is that the moment you start, and that is in many groups, I think I have been a member of at least 8 flat earth groups. There are 2 kinds of flat earth groups, no, perhaps 3. One is the groups for true flat earthers. Here you are banned or excluded almost immediately if you start to ask serious questions, put people's claims into critique and challenge people's claims. I, for example, got banned, I think, because I didn't get a reason, just for saying that people should stop with their conspiracy crap. Because I think it's crap. A conspiracy lives on only one dimension, and that is everybody is lying. And if someone tells you they're not lying, they're lying even more. So it's sort of a reinforcing statement. The more people try to convince you that the conspiracy is not there, there's no conspiracy, the more reinforced people, the conspiracy theorist or hypothesist, as I call them, or perhaps even conspiratards, the more they become reinforced in the idea that there actually is a conspiracy. And I've noticed that for many flat earthers, the conspiracy idea is what is holding up the idea. It's the foundation of the idea. It's not physics, it's not knowledge, it's not truth as somebody say it is. It's the conspiracy. Somebody is lying. Somebody wants to hide something. Alright, so that's one of the groups. The other groups is I would say actually like, that's my personal idea, but it might not be true. It's like Flat Earth Society, the large Facebook group in English, which is primarily globe earthers and some trolls. So that is probably why the same idiotic, stupid memes are going to be repeated over and over and again. And yeah, that's how it goes on. There are maybe one or two, handful of true flat earthers, but they are, when their point of views are being challenged, as I would say, they immediately seek the echo chambers where they are not reinforced. Where they're not challenged in their beliefs, but are reinforced in their beliefs. The third group, which I am still a member of, is the groups that are managed by globe earthers and primarily consist of globe earthers. Some flat earthers might sort of intervenely or at some point enter the group, discuss a little, but then quickly leave it again. So it's primarily globe earthers. And I find that really terribly annoying and terribly stupid. So that is why I sort of decided to to get myself a little bit away from that environment. I'm still active in it in some sense, but not entirely. Because I don't mind the discussions. I don't mind that people are challenging physics and the theories in physics. But the problem is, as I see it, is that flat earthers sort of reinvent their own ideas and then immediately conclude on no basis at all that their current theories are wrong. So the idea actually is, as I read at some point, that the reason why flat earthers do what they do is because they simply don't want to take the time, or perhaps even don't have the mental capacity to learn the theories in physics, the mathematics and so on. So instead of just concluding that, well, that's above me, I can learn that, they just conclude that it's fake, it's not true. And that also pisses me off a little bit. Alright, so the conclusion of all of this is that I might do one or two videos about flat earth. I think I have an upcoming video where I will discuss sort of one of the basic arguments I hear over and over again, perspective. and sort of put an explanation on why it cannot be perspective. Alright, so that was the announcement, sort of the basic announcement, just to say I have been away for a while, but I have not stopped doing these videos, particularly about physics. Alright, so what I wanted to discuss or tell you about in this video is something I find fantastically fantastic, and that is what I'm going to tell you about now. Alright, so just to recap, if you've seen my previous videos, you will sort of initially, quickly, hopefully, get an idea of what this is about. But just to recap what gravitational lensing is about and how we do it, I'm just going to shortly recap on it. Alright, so you probably already know that in a cluster we have some elliptical galaxies, we have also some spiral galaxies, and we might also have some irregular galaxies. These are all galaxies. So they are mentioned in the order of which they appear most. So in a typical large cluster, like for example this cluster I've been working on, MAX J0416/2403, there are lots of elliptical galaxies, a couple of spiral galaxies, and as far as I know there are no irregular galaxies. Not one that are mentioned, that is. Alright, so as you can see here, the galaxies, when we look at a cluster, we see it roughly like this, so in 2 dimensions. But as you probably can imagine, clusters are not living in a plane. They're not sort of just in the same dimension depth-wise or along the line of sight. So if we sort of looked at a cluster from the side, that is, there would also be sorry for my terrible there would also be some depth. Sorry for my terrible drawing. I'm not very good at drawing. And this is along the line of sight. So if you imagine what you saw before is if we took this like we saw it here and then flipped it over and looked at it like this, there would be some depth in it. Alright. But as you can probably also remember from my previous videos, one of the ways we modeled such a cluster was, or any gravitational lens system, is to use the thin lens approximation, which is that we basically say that all you saw here, all the things that are along the line of sight, so all the mass we just squeeze into a plane. And so we ended up with the basic lensing equation looking something like this. Right. And where this alpha here contained some length dimensions and all that. You can look at my previous videos if you want to know exactly. But this is the basic equation, and if we got to write it out, we have the background galaxy here, or source. Then we have the cluster here, and then us as the observer here. And so we said that this angle here would be the deflection angle, and this angle here would be the scale deflection angle. I might have it's been a while since I've worked with such a drawing, so this would be the image that we saw. And as you can see, this angle here is a sharp kink, and so we used the thin lens approximation and the small angle approximation to arrive at this conclusion, that we can treat this entire cluster as sort of a plane, the lensing plane or lens plane. Lens. This is the source plane. And this is the observer still. Alright, so this was the idea, right? That we can sort of squeeze all this mass into a single plane. Now we're still doing that to some extent. This is the really interesting part. Because this is an article that was posted at the 27th of June 2017. I'm not sure whether it has been received or accepted. This is an article by G. Shirivi, I hope I pronounced it correctly, and also my advisor at my master thesis, Claudio Grillo, and they have submitted this article to Astronomy and Astrophysics, the journal. And so the idea is, I'm going to read out the article title, and I'm also going to put the link, because it's on ArXiv, where you can read it if you want to. I'm going to put the link in the description of this video. But in any case, the title is MAX J0416.1/2403 Impact of line-of-sight structures on strong gravitational lensing modeling of galaxy clusters. So what does this mean? Well, in particularly around MAX, I'm just going to call it MAX from now on. We knew, and I hope I can remember the redshifts correctly. So the redshift of the cluster, sorry, that should have been a set. Let's just keep it here to remember it. So the redshift of this cluster, this is going to be terrible, like that, is 0.396, I think it is. But we also know that there's a galaxy somewhere here at the redshift of 0.112. And why is that galaxy important? Well, that galaxy is important because when we look at the, I've made a video about my master thesis defense, where I am pretty sure I've put a picture up on of the cluster MAX here. But the thing is that we have a galaxy here somewhere a little bit to the south of the main part of the cluster. And we know this galaxy is important because there's lensed images around it. So what does that mean? That means that we cannot be entirely sure that this galaxy does not perturb these lensed images a little bit. So if we sort of just took it out of there and said, well, we don't care, and try to model it, we would get a worse result. And that is also reflected in the models they made here. I'm just going to read some of the the results they got. So I'm going to continue with the explanations, but just to set the scene. All right, so they have run several models. They have run one model where they model the entire cluster as a single plane, but then add this galaxy there. And the error they got, and that is the root mean square error on all the images. So if you take the predicted images and compare with the actual images, then you get an error. Unless you have a terrible good model, then you get an error. As you hopefully can remember, just to recap how we did the modeling. So the way we model such a lens in any type of lensing code is that we look at the images that we have, and we put in some potentials in here at the lens. 20, 2, 1 potential, doesn't matter. Then we say, all right, at this given potential and the image here, let's put in some mass in there, some parameters, and then check where will the source be. That's one way to do it. And then we do it with all the images, all the way across, and then we get different positions of sources. And then we try to find what is how much do they differ, and then we try to get them as close as possible, and that will be an indication of the chi-square and the error in itself. But the problem is that comparing with this model is insanely fast. As you can hopefully remember, the lensing equation is beta is the position of the source, theta is the position of the images, and alpha as a function of theta is the deflection angle that we see. This is where we see the images. Alright, so just to recap that. So when we want to find the source position, we can just calculate the equation as it is. Of course, we cannot do it exactly in a computer. We cannot do it exactly as it is here. But the idea is that we don't need to invert the lens equation. As you probably can imagine, as you probably can remember, that if we wanted to invert the equation, let's say we wanted to check the position of the images, we would write something like this. Let me see. So here we would have theta is equal to the position of the source plus the deflection angle, which is dependent on theta. Now this is a false equation. You cannot calculate that. It's wrong. And this is why the lensing equation, as I've said in several of other videos, I think at least one, is an nonlinear equation. So in this state you can calculate it, you can invert it, you cannot calculate it, at least not analytically. You can do it numerically by doing several models. Alright, so calculating the source position and then comparing how much they differ is easy and it's fast, but it's also wrong. Because we are trying to compare, think about it, the only data that we have actually is the position of the potentials, of course. But the only data we have to compare with is the images. So what we do then, which is a lot slower, is that we invert the equation, then we try with some model, put in some parameters, find the source position. and then backtrace that source position to say, well, at a given source position, how many images will there be and where will they be? So that's the basic idea. And the reason why this is a lot slower model, the way of doing it, is because let's say we do this model here and get the finest result of the source position. We calculate the lens equation in the source plane and get, let's say, a chi-square completely equal to the number of the degrees of freedom, the number of degrees of freedom. And that is a very good chi-square. That is almost a perfect model. Then we invert that model, use that same source position, or those source positions, with that same cluster parameters, and then we might end up with a terrible result when we compare it with the images. We might even get more or less images than we actually have, so less predicted images or more predicted images that we have. So that is the sort of that is the indication, or the sort of the way of showing that the lens equation is nonlinear. All right, so that's the idea. So the thing is that when we cannot know whether this galaxy here has an influence, we need to include it. And so there are two ways of doing that. The first way is to, the way it has been done so far until this article came out, and a little bit before because they actually have to, to develop the code, but the way they did it before was to say, well, we are not interested in the mass of this galaxy. We just want to include it to perturb the images. So we say, all right, well, we just switch it to the same redshift as the cluster. And when we get the parameters, we are immediately aware that they are nonsense parameters. Just to exclude them, we just need the model to get the mass of the cluster. And we need it in order to include it because we think that it might have perturbed the images. So doing that, shifting the cluster to the redshift, shifting that galaxy to the redshift of the cluster, and in this article they got an error of 0.19 arc seconds. RMS. Just two weeks. So what is that number of representation of? So when we do the lens equation, we invert it, and then we get some prediction of the images. They differ. So the predicted images differ from the position of the images that we can see, and because of that difference, we get an error in arc seconds. So when we do that with all the images that we have, and in this case it's quite a number of images, I think it's over 100 images they have, we of course can calculate the root mean square of all those errors, and that is what that number is. So this represents sort of the root mean square of all the errors of all the images, all the predicted images. All right. So they also did it excluding this galaxy here at all. Just take it away. And that gave an error of 0.32 arc seconds root mean square. So this immediately tells you that we need this galaxy perturb the images, because otherwise these two numbers here would be relatively the same. Not exactly, but relatively close to each other. But there's a factor, there's a real difference between them. All right, so that's the way we also in my thesis and many articles so far has done this kind of calculation. And the problem is if we just wanted the mass of the cluster, and that is evident when you look at the results of the masses they got here and they compared, this is not so important. We can include this galaxy here, and we get a reasonable mass estimate. But the thing is, we want to find also, let's say we have some distances, right? Alright, so let's put it in the distances. We have distance from the observer to the source. Let's call that DOS. Then we have the observer, the distance from the lens to the source. Let's call that DLS. I think I called it something different in my other videos. And then we have the OL, the distance from the observer to the lens. All of these distances here are dependent on the cosmological parameter values. So in this case we have the Hubble constant. Let's just call it Hubble const. We have omega matter, and we have omega lambda. And so omega matter is a combination of baryonic plus dark matter. And as I remember them on top of my head, the Hubble constant is 70 kilometers per second, per second per megaparsec. Omega matter is roughly 0.3 and omega lambda is roughly 0.70, so it's 0.7. So since these distances here are dependent on the cosmological parameter values, we can also say the opposite, that the cosmological parameter values are reflected in these distances here. Now, the way we calculate some of the distances means that we divide the Hubble constant by the Hubble constant. So this is not a part of these calculations. We cannot infer the Hubble or derive the Hubble constant from the distances. But we can try to calculate or optimize these parameter values here. And again, here comes the problem, because our sources are dependent on, first and foremost, what we call matter along the line of sight. That can be anything. Structure along the line of sight, it's also called. But also both galaxies in the foreground, but also galaxies in the background. So that means galaxies in front of the cluster that can perturb the images, and galaxies in the background that can perturb the images. So because we're cheating when we are saying, well, let's take those galaxies here, actually the background galaxies that they have found here are not part of any of the calculations that have been, or modeling that has been done previously. So let's just exclude them for a while. But we are basically cheating by putting this galaxy at the same redshift of the cluster. And that means that we cannot in any way, just by optimizing these parameter values here, we cannot estimate them in any true sense. I'm currently working on an article together with one of the people that helped me write or advised me when I wrote my master's thesis. We're working on an article which we will publish in in some time in the future that deals with this problem in a different way. We are going to use statistics in comparing different masses and so on to actually derive the cosmological parameters, which is completely independent on this problematic here. But still, in order to do this kind of calculation, this kind of optimization, but also in general to get a better model, we need to include these both foreground and background galaxies at their true redshift. And here comes the thing. So let me show you how it works. So let's say that we have a background galaxy here, a background galaxy here, a cluster here, and a foreground galaxy here. So the ideal way to do this would be to say, well, we are here observing. We have the background galaxy here. This is, sorry, the source. Then we have some, let's call it background 1, background 2, and foreground 1. So the ideal way, the best way to do this would be to say, well, the light from this source here will reach this galaxy here, then be a little perturbed, then reach this galaxy here, be a little perturbed, then reach the cluster, then reach this here, and then be a little perturbed again. Just going to put in the places where we have this perturbation. And so instead, before, let's just put this in like something like this. So before we would have the source, let's say relatively here. But instead we are now going to get the position of the image somewhere up here. Let's just do it like this. There you have it. This is just a rough explanation. This is not in any way representative of what would actually happen. It's just to show that when we did the ideal way to do this would be to include all of these background galaxies as perturbing the light from the source just a tiny bit. Not much, but a tiny bit. Enough so that we would actually shift the images just a little bit. Alright, so here it comes. With that in mind, let's look at the differences of the lensing equation. Or at least one way to sort of formalize this difference. So the new lensing equation, adding this, let's call this single lens plane. So this is the formalism for the single lens plane. This is the formulation of the multiple lensing planes. And it would look like this. So we have theta of j, theta 1 is equal to theta 1 minus the sum of I equals 1, j minus 1 of dij over dj alpha as a function of theta I. So the idea here is that we have multiple lensing planes, right? So we have all these galaxies, and all of them perturb the images just a little bit. They shift the images. We treat them as actual lenses, but then say how much do they shift the images around, and then we sum up all of those perturbations in a single calculation. And so we get the deflection angle here, which we now call alpha tot total is equal to, again, the sum of I equal to 1 n minus 1 of di n over dn alpha. I think that should be like this. No, something like this. Theta I. Cos, yes, like this. So as you can see, we sum up all of the images, all the deflections that we have. That's the basic idea. Instead of treating all this as one deflection, just take all of it, put it in a single point, and they say that's the deflection. We take all of these lensing planes. So let me give you an idea here. Let's make a little drawing. So the first drawing that we saw was that we have the lensing plane here, the observer here, and the source here. With multiple lensing planes, it just makes something wild. We have the source here again, then we have a lensing plane here, a lensing plane here, a lensing plane here, and a lensing plane here. Now this is completely and wildly exaggerated. This is not how it would look. For example, this would be highly highly improbable that we sort of would get a lensing like that. Let's try to make it more probable. We could get something like this. Something like that. So we can add several numbers of lensing planes and then calculate it for them. Now this also means when you actually do the model that you need to put your lenses, your planes, your galaxies in a specific number. In Lenstool you start, and I guess the same is for GLI, which they've used in this article, you start with the lowest redshift and then work your way down towards the highest redshift, and then you calculate it that way. I'm not entirely sure whether they invert it, so they take the highest redshift and then goes towards the lowest redshift. That might make some sense, but remember that when we invert the lens equation, we actually try to do the reverse, so it goes both ways. Alright. Let's try to mention some of the results that we get using that. I can just let you look at this for a while, and then let's call it multi. Like this. This is multi-lens planes, or multiple lensing planes, whatever you want to call it. Where we basically do the same thing. We still treat all of these lens planes as a thin lens, but we do it with multiple thin lenses. That's the basic thing. But as you can see here, using a single lens plane, we just treat all of it at this lens plane here. So let's call that L. Here we have L1, L2, L3, and L4. So we say how much does L4 perturb the images or shift the images, how much does L3 perturb the images, how much does L2 perturb the images, and how much does L1 perturb the images. And then the lensing code will itself figure out, well, you put in some because we still use the results we have from the single lens plane. As you can remember, like I said, this will not change the overall mass of the cluster in much, actually. But it will change the errors we get on the image positions. So we can use the parameter values that we have from the single lensing plane model as sort of a template to work towards the multiple lensing planes. So if we have, let's say this is the lensing plane with the cluster, we would still have that it is the cluster, it's the lens where the most mass is. We would still have that this creates the images, but these other parts perturb the images a little bit. The code will figure that out on itself. Alright, so let's get some results. Okay, so like I said, Siviri et al. And others have conducted several models. Let me just list them. I'm not going to write them up, I'm just going to tell you. So they have what they call MP4. So that means that they include, let me just see where it is. Here it is. So they have found, let's say the cluster is at 0.396, the redshift. So they have found 3 galaxies in the foreground. They have one at 0.1124, that is the one that is present in most of the models. Then they have found one at 11.26. And then they have found one at, 0.1124, 0.1126, and 0.1533. So those are foreground galaxies. The background galaxies, and this is beside the normal perturbers that you add. I think we are on 194 perturbers now, but excluding those, we also have a perturber at 0.4678, the redshift, 0.4848, 0.5004, 0.5277, 0.5376, 0.7093, 0.7358, and 0.7362. Including all of those, including the clusters, the cluster halos and all that, including the cluster members, the galaxies, and all of those. This is what they call the MP full, so the multiplane full. And then they also have a model they call SP1, single plane 1. This is the model that has been used so far, the model where we have a galaxy, the cluster, and then the foreground galaxy, but shifted at the same redshift as the cluster. Then we have SP, single plane. This is the same model, excluding that galaxy. Then they have MP4, not 4, but 4 like foreground. That is the multiplane using only the foreground galaxies. Then they have MP back, which is the multiplane using only the background perturbers or background galaxies. And then they have 2 where they call constant ML and constant ML. That's mass to light ratio. They use them constant. All right. So for the MP full galaxy, they get an RMS of let's just say RMS error on the images. That's what we get here. They get 0.08 arcseconds. This is an extremely good result. Extremely good result, I would say. Alright, so for the SP1, that is the single plane model with the foreground galaxy shifted to the cluster position, they get 0.19. This is something completely different, right? This is higher. So the models I have been working on so far, using also, because let's just get that straight away. In this model, in this article, they have used the lensing code called GLEE or something like that, GLEE. I just call it GLEE. Whereas the lensing code I have worked on or used is called Lenstool. And so I think just a little bit before this article was out, I got an email from the man currently mostly responsible. He's actually in any case, he's sort of the outward face for Lenstool. He's the one I received most messages from and have asked most questions. Got an email from him saying that they were ready with a new version of Lenstool that included multiple lensing planes. Alright, so the designers of GLEE came a little bit before, but Lenstool came just after. So using Lenstool and using multiple lensing planes, but only using the foreground galaxy at the correct redshift. So I have, let's just put a line here. So for these models, we have yeah, let's just put one in, because we also have results using Lenstool. But mind you, that when we are running Lenstool and also when they're running GLEE, we use a Bayesian approach. I'm not going to bore you with that because I've already made a video where I get sort of into the sort of superficial explanation of the workings of such a model. But the thing is that when doing such a model, you decide how many samplings you want to run. So the more samples you run, the more you test your parameter space. Now, I think that I haven't read it that carefully, and I'm not sure it is in this article, but I think the usual approach for the GLEE model is to use something like 10 to the 6th samples. And the models I have run so far, one uses 1500 samples and the other uses 1000 samples. So with that in mind, I want to run all of these using 20,000 samples. Just because it takes way too long to run 10 to the 6th samples. But the results we got that are preliminary is using the same model as this one, roughly, just in Lenstool. We get an RMS, let's call that SP1, 0.92 arcseconds. And the best model where we add, so in this model here, we have the foreground galaxy, let's just call it FG, We have that at redshift 0.112, and we have the cluster still at plus the perturbers or the cluster members at 0.396. So not all the galaxies that they have in this model, just the foreground galaxy, but at the correct redshift. We get, let's call that MP4. We get 1.00 RMS. But remember that this model here is with 1500 samples, and this model here is with 1000 samples. So the reason why, and just to recap why I do this, is when I start to run such a model, I first run it using source plane optimization, because it's fast, to narrow in the parameter space, so to get a guesstimate and a best idea of what the best parameter values are. It not always it works with all the parameter values, but usually you can get an idea. And from there, I run several models now using 1500 samples to, and that was before I ran that. I chose, when I ran this model here, I chose 1000 samples. But I have later found that 1500 samples is better. And you might ask yourself, well, why have you run this at 1500 when you ran this later? That's because I ran this after those. So this is my comparison model. I am also working currently on an MP4. But since there's a lot of things going on in here, and I have to expand some of the parameter values, I'm currently running it in image plane optimization, but it takes a heck of a lot of time to narrow that field in. So this might change a bit when I get both of those up to 20,000 samples, and then I can get back to you with the results. So what we can say from this is, when running this model using GLE, there's a significant difference. Totally. Now, I'm not sure how GLE works, but the thing is that Lenstool works like this, and that's because it's a little complicated to run such a model like this, is that you can put in specific or individual potentials. Let's say we have the cluster here, Halo 1, cluster Halo 2, and then we have the potentials, which is the cluster member. So this is the 194 galaxies, I think it is. Something like that. So before that potential, and this is at the same redshift as the cluster, before that I can put in as many foreground galaxies let's call it I. As many foreground galaxies as I would like. But the problem is that I can't, after I put in this potential here, this is a file that you put in, I cannot put in more galaxies here. That won't work. Lenstool will simply not include them in the calculation. So what I have to do is to include more potential files. Let's just call them pod files, but with background 1 down to background J, like that. And these galaxies here I'm pretty sure of, because those are just individual potentials. but I'm not sure about these galaxies here, because all the potentials in here are dependent on the scaling relations, and so all the background galaxies that I put in here are also dependent on the scaling relations. But time will tell in what happens. But what I wanted to sort of address in this video here is that with this article here, and also with hopefully with the results I get from Lenstool, we are entering what I would describe as a new era in gravitational lensing calculations, because now we can actually add galaxies, both foreground galaxies and background galaxies, at their correct redshift. So we can actually get much closer at modeling these systems as they truly are. Now, we are still dependent on some assumptions, for example, approximations, the thin lens approximation. We still use that, use it multiple times, but we still use it, and we also still use the small angle approximation. But those have turned out to be completely valid in several occasions, so I'm not so worried about that, but I think it's good. And I'm very excited about it. I may not look like it, but I am actually very excited about it, because this means that we can hopefully get a lot of new good results using Lenstool, gravitational lensing. And also, if we combine that with the new ability that we have now, which I might do another video about, perhaps, using gravitational waves to explore the universe. So, just a short appetizer around that. The way we have explored the universe so far has been the same way that you see me now using electromagnetic radiation. That is light, both visual and non-visual, that is radio waves, microwaves, gamma rays, X-rays, all that, but they are still electromagnetic radiation. So it's like, although we have a wide span of different types of electromagnetic radiation, it's still sort of like looking at the universe using one eye only. Now we have opened up for the second eye. We can explore the universe not by looking at how light is coming, but how objects in the universe are actually influencing space-time itself. But that's a discussion, that's a topic for a completely new video. I'll just end this video by saying thank you very much for watching. I will get back to you when I have hopefully better results than this, perhaps even when this model is finished. And of course, I will also get back to you when the article I'm working on currently is hopefully published and accepted and all that. So I'm just going to say I think it's really exciting times for astronomers and astrophysicists working with gravitational lensing. So thank you very much for watching. Bye.